Welcome everyone to my podcast. I am Dr. Saju Divakar. I'm a radiation oncologist with over 23 years of experience treating cancer patients with radiation therapy. In today's episode, we are exploring the captivating journey that led to the discovery of X-rays, a breakthrough without which modern radiotherapy wouldn't be possible. It's a story that began with the experiments in static electricity and culminated in one of the greatest medical advancements of all time. Imagine a world where diagnosing a broken bone required nothing more than educated guesswork, where peering inside the human body was a pure fantasy. Today, we take for granted the ability to see within ourselves using X rays, but this incredible technology is relatively recent. It arose from a series of curious observations, chance moments, and the efforts of some truly brilliant minds. Let's journey back to the 17th century. Picture bustling marketplaces and lively fairs where people gathered not only to trade but also to be entertained by spectacles that defied their understanding of the natural world. Among these wonders were demonstrations of invisible forces, the mysterious effects of static electricity. Performers and early scientists thrilled crowds by making sparks fly from their fingertips, causing hair to stand on end, and moving lightweight objects seemingly on their own after being rubbed with certain materials. Today we know this as static electricity, the buildup of electrical charge on surface of objects. But back then it was a source of endless fascination and even considered magical. It sparked genuine scientific inquiry. In the 18th century, scientists began experimenting with ways to harness this mysterious force. One of the most significant inventions of this period was the Leyden jar. Essentially, it was a glass jar with metal foil inside and out, capable of storing static electricity. This was the first device that allowed scientists to conduct experiments with stored electricity, a primitive capacitor of sorts. These devices weren't confined to laboratories. They became popular in public demonstrations. Showmen would charge the Leyden jar and invite volunteers to experience a shock astonishing onlookers. Some even believed that these shocks could cure ailments. Electric doctors roamed the streets offering treatment for headaches, arthritis, and more. While we now know these claims were more showmanship than science, these early experiments paved the way for serious research into electricity's effects. As we move into the 19th century, the pace of discovery accelerates. In 1800, Italian physicist Alessandro Volta made a groundbreaking advancement, the invention of the voltaic pile, the world's first true battery. This device allowed for a steady, reliable flow of electric current, making a major leap forward. With this continuous source of power, scientists could conduct longer and more precise experiments. British chemist Humphrey Davy utilized Volta's invention to split compounds into their elements through electrolysis, discovering potassium, sodium, and other elements. This was no longer the realm of single sparks or fleeting discharges. Electricity had become a tool to unlock the secrets of matter. Michael Faraday, a towering figure in the history of science, took things even further. He demonstrated that electricity could produce magnetic effects, leading to development of electromagnetism. Faraday's work revealed connections between electricity, magnetism, and chemistry, insights that would prove transformative for future technologies. In 1807, Davy demonstrated the first arc lamp by passing a strong current through air between two carbon rods. The resulting bright arc showed that electric currents could flow through gas, producing light and heat. This phenomenon required high voltages and led to ionization of gas, a key concept for later developments. Around this time, scientists started experimenting with electricity in gases, observing how electric currents could pass through air and other gases, creating glowing effects. However, to study these interactions properly, they needed a controlled environment where they could manipulate pressure and composition without interference. This led to the work of Heinrich Giesler, a German glassblower and physicist who in 1855 invented the mercury vacuum pump. This innovation allowed scientists to create low-pressure environments inside glass tubes known as Giesler tubes. When electricity passed through these tubes filled with various gases, they emitted a glow. These experiments produced beautiful colors, and indeed, today's neon signs are modern descendants of these early experiments. Building on this, British scientist William Crookes developed the Crookes tube in the late 1870s. Using a stronger vacuum, Crookes observed something even stranger: mysterious cathode rays streaming from the negative electrode or cathode in the tube. These rays cast shadows and could be deflected by magnets, suggesting they were particles with mass and not just light. The nature of cathode rays sparked intense debate. Some scientists believed they were form of light, while others argued they were streams of charged particles. This debate set the stage for discoveries yet to come. German physicist Philipp Lenard had modified the Crookes tube to create the Lenard tube by adding a thin aluminum window that allowed cathode rays to escape into the open air. He noticed that these rays could produce fluorescence on the materials placed outside the tube and could penetrate thin sheets of metal. However, he didn't fully explore these observations, and the significance of his findings went unrecognized. Lenard's focus was on understanding the cathode rays, and he didn't realize that he was on the brink of a groundbreaking discovery. Other scientists noticed odd effects as well: photographic plates fogging mysteriously, materials fluorescing unexpectedly, but they often dismissed these as experimental errors. It was as if the discovery of X-rays was hovering on the edge of scientific awareness, waiting for someone to notice the big picture. That someone was Wilhelm Röntgen. On the evening of November 8, 1895, Röntgen, a professor of physics at the University of Würzburg in Germany, was conducting experiments with a Crookes tube. To prevent light from interfering with his observation, he covered the tube with black cardboard, leaving himself in a darkened room. As he powered up the tube, he noticed something extraordinary. A nearby screen coated with barium platinocyanide began to glow faintly, even though it wasn't in the direct path of the cathode rays. Röntgen was baffled. How could the screen be glowing if no visible light was hitting it? Driven by curiosity, he began experimenting systematically. He placed various objects between the tube and the screen: books, wood, metals, and discovered that this mysterious radiation could penetrate materials in ways that light could not. Some objects blocked it, while others allowed it to pass through. In a pivotal moment, he placed his own hand between the tube and the screen. To his amazement, he saw the silhouette of his bones projected onto the screen, surrounded by the faint outline of flesh. Röntgen had just taken the first X-ray image of a human hand. Röntgen spent weeks repeating his experiments and documented everything meticulously. On December 22, 1895, he asked his wife Bertha to place her hand on a photographic plate. When she saw the resulting image, her bones starkly visible with her wedding ring shining bright, she reportedly exclaimed, "I have seen my death." It was a profound moment, a Christmas miracle of science, offering a glimpse inside the human body that had never been seen before. He quickly published his findings in a paper titled "On a New Kind of Rays," calling them X-rays, with X signifying the unknown. News of his discovery spread rapidly. Within months, scientists, doctors around the world were replicating his experiments. Hospitals began using X-rays for medical imaging. For the first time, physicians could see broken bones, foreign objects, and other internal conditions without making a single incision. Röntgen's discovery transformed medicine almost overnight. But the story didn't end there. His work inspired French physicist Henri Becquerel to investigate whether other materials like fluorescent minerals emitted similar rays. In 1896, Becquerel discovered radioactivity by accident when he noticed that uranium salts could expose photographic plates without any sunlight, a groundbreaking observation revealing that uranium emitted radiation on its own. Marie and Pierre Curie were captivated by Becquerel's findings and delved into the study of radioactive elements. By 1898, they had discovered polonium and radium, introducing the world to new elements that emitted powerful, spontaneous radiation. Marie Curie even coined the term radioactivity, forever changing the landscape of nuclear physics and atomic science. So, was Röntgen simply lucky? Perhaps, but as the saying goes, chance favors the prepared mind. His curiosity, meticulous experimentation, and willingness to explore the unexpected turned a very accidental observation into a monumental discovery that changed the world. This story reminds us of the beauty of science, that sometimes the greatest breakthroughs happen when we are open to the unknown and ready to pursue it. The discovery of X-rays not only revolutionized medicine but also paved the way for modern physics and our understanding of the atomic world. Thank you for joining me today on this journey through history and discovery, has given you a deeper appreciation for the technology that plays a crucial role in modern medicine, including radiation therapy.